Hello friends, welcome back. Today I came across this question number 6, paper 2 JEE Advanced 2020. This is a question from thermodynamics and I'm quite intrigued by this question, though it has got a dead end, but let's solve this problem. So what's given is there is a cylindrical vessel of height 8 meter and it's kept vertically. Along with that, it's given that there is a partition which is dividing the cylinder in two chambers. We are calling them A and B. And initially the partition is exactly at the center, so it divides the two chambers of height 4 meter each. Initially it is held there and later it is released. Other than that, it is also given that the number of moles in each of these chambers of the ideal gas are 0.1 and initial temperature is 300 Kelvin. Mass of partition is also given 8.3 kg. So definitely it means that the partition is initially not in equilibrium. It is being held there. After releasing, it's going to come down. So other informations are thermally isolated closed vessel. This vessel is thermally isolated. It means it implies that there is no heat transfer via the walls of the cylinder. They are thermally isolated. Also, the partition is diathermic. It means the conductivity of the partition is very high. The heat transfer between A and B chambers is going to be so fast such that A and B are always in thermal equilibrium. It means TA is equals to TB. Now, my friends, there have been some misconceptions in the solution of this problem. I'll discuss about two of them. First one is the common mistake which has been made by the students is they have assumed that the temperature is not going to change between A and B. I'm sorry, the temperature is not going to change with time for both the chambers A and B. It's going to remain 300 Kelvin throughout the process of falling of the partition. But that is not true to assume. The only thing which we can assume based on this diathermic partition is that the temperature of A and B are going to remain same throughout the process. It does not mean that it is constant also. Because you see, the gases can do work on the partition. The partition has got mass, it can store kinetic energy. There can be energy transfer between the gas and the partition. We can't say that the temperatures, the internal energies of the gases is not going to change. The second misconception about the question, about this I found in the solutions, is the gravitational work is also being converted into the internal energy of gas. Well, it is clearly mentioned in the question that the partition is frictionless. If the partition is frictionless, how can work done of the gravity be converted in the form of internal energy? There must be friction to transfer that energy in the form of internal energy. Now the question is, where does that energy go? Where does the work done go? Well, that will increase the kinetic energy of the partition. While the partition is in equilibrium, it does not mean that the velocity of partition is zero. In equilibrium means the net force is acting on the partition at equilibrium is zero. So it can possess some kinetic energy. So we should not consider the work done while writing the work done of the gravitational force while writing the first law of thermodynamics, because it's not going to raise the internal energy of A and B, as there is no friction between the walls of the cylindrical vessel and the partition. So let's deal with these two chambers separately so that we can write the equations of first law of thermodynamics for each one of them. Let's say heat transferred to A is given by dq at an instant when the partition has fallen by a distance x. And let's say at this particular instant the work done by the gas on the partition is P dV or I'd rather say PAdV, where P is the pressure of the chamber A and dV is the change in volume of chamber A. So we can write the first law of thermodynamics equation for chamber A as heat transfer to chamber A is equals to change in internal energy of this chamber plus PdV work. Okay. And now let's consider chamber B. Well, it is known that the heat transfer to chamber A can only take place through this partition. It can't take place through the walls. So whatever heat is given to A has been taken from B. So I can say that heat taken from B is dQ. And let's say work done on this partition by the chamber B is pressure PB into volume would be minus dV. We are saying that dV is change in volume of A, so minus dV is going to be the change in volume of B because it is going to decrease. So let's establish the equation of first law of thermodynamics for chamber B. Heat transfer, now heat has been taken out, so I'll use minus sign for this, is equals to, now this is very important, at any point of time temperature of A and B are going to same. The number of moles in A and B also same. So I can say that the internal energy change at any instant is going to be same for A as well as for B. Plus work done by the gas is pressure of the gas, and we have seen that volume is decreasing, so there's a minus sign, minus dV. Let us consider that the surface area of the cylinder is S. Then I can say that dV is equals to nothing but S into dx, but dx is further drop of this partition at this particular instant. So I'll substitute this and consider these two equations as equation number 1 and 2. Let's add these equations and we'll find that 0 is equals to 2 times du plus Pa minus Pb, and dV can be substituted as surface area into dx. So we'll write 2 du is equals to Pb minus Pa into surface area into dx. Now du can be written as number of moles into Cv into small change in temperature at this particular instant, and this is equals to Pb. At this particular instant the pressure can be found by ideal gas equation. Pb will be number of moles into R into T divided by the volume, which is going to be surface area, into the volume at this particular instant for chamber B is going to be, you see, 4 minus x. 4 was the initial height of this chamber, and x, it has decreased by x because of the drop of this chamber, this partition. So the height will be 4 minus x into surface area. This gives you volume. So nRT by V is the pressure PB. Similarly, I can find the pressure of chamber A. Number of moles same, R same, temperature at a particular instant, T, let's say. The volume would be different, surface area is same, only the volume has increased here. So it's going to be S times O plus X into surface area into dx. I can cancel out this S now, it was not required. You can also cancel out this 0.1. Now clearly this equation requires integration. So 2 times Cv by R dt by T is equals to, by solving this, 2x divided by 16 minus x square and a dx. Everything else is adjusted. And now let's integrate. Initial temperature was 300, we know. Final temperature, let's say TF. And here the initial displacement of the partition was 0. Final is, let's say, XF. After integrating this, I can say that 2 CV by R ln of TF divided by 300 is equals to, integration of the right hand side is ln of minus ln of 16 minus x square, and the limits are 0 to xf. So 2 CV on R ln is equals to natural log of 16 divided by 16 minus xf square. So now we have an equation between TF, final temperature, and final displacement. So it can further be simplified as TF on 300 to the power 2 CV by R is equals to 16 upon 16 minus xf square. So let's call this equation number 3. At last, we know that the final condition we are talking about is a condition of equilibrium as asked in the question. And while the partition is in equilibrium, the forces, we have drawn the free body diagram. There's a pressure force of chamber A, there's a pressure force of chamber B, and there's a gravitational force of the mass of the partition itself. So by balancing this, I can say that pressure force, final pressure force, that is during equilibrium, into surface area plus mass of the partition into gravity is equals to final pressure force in the B chamber and its surface area. Now again we are going to use ideal gas equation to substitute PAF and PVF, and that is going to be number of moles R, final temperature it's going to be same for A and B, divided by volume is going to be, for A it is going to be 4 plus XF times surface area into surface area plus M is given as 8.3 into 10 is equals to 0.1 R, final temperature chamber B, volume is going to be 4 minus XF times surface area into surface area. Now we see that surface area is getting cancelled out, and here we get a second equation for relation between final temperature and final XF. So some things can be cancelled out. R can be cancelled out by 8.3. So it's going to be 0.1 TF or I would send this term on the right hand side, and I am getting on the left hand side 10 is equals to 0.1 TF coming common, 1 upon 4 minus XF minus 1 upon 4 plus XF, that would be like 2 XF upon 16 minus XF square. Now TF can be substituted from the previous equation. I'll rewrite the previous equation here. We got TF divided by 300 to the power 2 CV by R is equals to 16 upon 16 minus xf square. Now remember, in the beginning I said this question has got a dead end. Yes, it has got a dead end for those students who are solving in the exam hall, because first of all, it's not mentioned what kind of gas is it. It's not mentioned whether it's monoatomic or it's a diatomic. So you don't know the value of CV. Even if you make some assumption, even if you say it's a monoatomic, so you want to write CV equals 3 by 2R, or maybe you start with diatomic and you say CV equals to 5 by 2R, still it is not possible to solve this equation in exam using the high school mathematics. It requires iteration, and here we are going to do that part also. We'll get the answer. So by substituting TF in this equation, I can say 10 is equals to 0.1 times TF is 16 divided by 16 minus xf square to the power R by 2 CV into 300. So this is TF, and the remaining portion of the equation, that is 2xf divided by 16 minus xf square. Now we have got equation only for xf. So we have got the answer using iteration here, but again consider two cases. Case 1, it's a monoatomic gas, and that means C is equals to 3 by 2R. So for this, after iteration, in fact we used calculator for iteration, xf is equals to 1.89, approximately 1.9. And if I consider a case 2 of diatomic gas, then CV is going to be 5 by 2R, and for this case the result is much different, approximately 1.93. So you see, the answer is not varying much, as the question is of the integer type. The correct answer to this question would be, they are asking the height of the partition from the top, so it's going to be 4 plus xf, and that is going to be 5.9 approximately. So if I want to use an integer to represent my answer, it's going to be 6. But JEE has awarded marks to all the students. You may call it fortunately, you may call it unfortunately. And the reason behind this, according to me, I believe, is it is not possible to solve this equation without iteration. Or it's not possible to solve this equation in exam using high school mathematics. So students got stuck there if you have solved by this method. But this is the correct method. And the correct answer to this question is going to be 5.9. It is not varying much if we vary the case of whether it's a monoatomic gas or it's a diatomic gas. So I hope you find this solution quite helpful. Thank you very much.